this video, we're going to talk about the stability of carbocations. So on the left side, we have a carbocation that is attached to 3 other carbons. So because it's attached to 3 other carbons, this is considered a tertiary carbocation. Now, what we can also have would be a carbocation that is attached to 2 other carbons, and this would be a secondary carbocation. If the carbon with the positive charge is attached to only 1 other carbon, then it is going to be called a primary carbocation. And if the carbon that has the positive charge is attached to no other carbons and only hydrogens, then it is going to be called a methyl carbocation. Which one of these is more stable? You need to know that the tertiary carbocation is more stable than the secondary, which is more stable than the primary, which is more stable than the methyl. So the more carbons that you have around your positively charged carbon, the more stable it is going to be. Now let's go over this example. Let's say you have a carbocation, and on one of them you have a methyl, and the other one you have an alcohol group. You have an OH. Which of these is going to be more stable? So let's explore that question. We know that tertiary carbocations are pretty stable in and of themselves. However, let's examine this carbocation that has an alcohol group attached. If you draw resonance structures for this compound, you can see that what can happen is that, let's back up here. One of the lone pairs in the oxygen can attack this bond and form a pi bond. And then, since the electrons would be moving toward this carbon would lose its positive charge. So the structure that you end up getting would be that these electrons form this extra bond here. The oxygen is going to lose a lone pair. So because the oxygen lost a lone pair, now it's going to be positively charged. Previously it had 2 lone pairs, now it has 1. And the carbon is no longer positive. The oxygen now bears the positive charge. Because of this resonance structure, this right here is going to be more stable than this. Now let's explore why. On the situation on the left, this carbon has 3 bonds, and each bond has 2 electrons. So 2 times 3 is 6. This carbon has 6 electrons. Now there's a concept called the octet rule that says that every single atom, not every single one, but most of them, including carbon, want to have 8 electrons in their valence shell. Currently, on the example on the left, the carbon has 6, so that means it's going to be unstable. However, on the right side, you can see that the carbon has 1, 2, 3, 4 bonds and has no lone pairs. So if it has 4 bonds and each bond is made of 2 electrons, it means it has 8 bonds in total. So the right side structure, this has a resonance structure that follows the octet rule or obeys it. And so it's going to be more stable than the example on the left where it cannot obey the octet rule. Let's go over a series of examples where we're going to have some carbocations in rings. Now go ahead and try and figure out which of these rings is going to be most stable when it comes to carbocation stability. So first off, this is going to be the worst one because it doesn't have a lot of resonance structures. It's just what it is. The one on the right, the top right, if I move it a little bit to the left so we could draw some resonance structures, you can see that what can happen is that the pi bond, the electrons in this pi bond, can move over toward the positive charge, and this would throw the positive charge 2 carbons toward those electrons. So a resonance structure of this would look like that. So this has one resonance structure, or actually it has two, because 1, 2. The one on the bottom left, if you analyze its resonance structures, it has 2 double bonds next to the positive charged carbon. So it can actually have a situation where this pi bond goes here, and then the positive charge jumps 2 carbons clockwise, and the other double bond stays the same. It can have another resonance structure because of the fact that it has 2 double bonds, where these electrons move toward the positive charge, and the positive charge moves counterclockwise 2 carbons bottom, and then the other pi bond stays the same. Now when it comes to this situation, this is going to be most stable because it has more resonance structure. So let's draw a few of them. What can happen is that, once again, a pi bond can move 1 over, and the positive charge moves 2 over. So you can have this kind of situation, and I forgot to draw the NH group, so give me a minute. So that's one resonance structure. You can also have a situation where it's reversed. But then the most stable resonance structure in this is actually going to be where it could happen off of both of these. We're running out of space a little bit, but I think we're okay. This positive charge can move toward the nitrogen, and then the nitrogen can give its lone pair to form a double bond here. So as you can see, in this situation, no carbons have positive charges, and the nitrogen is the one that bears the positive charge. And it's going to be most stable because now all of the compounds, or not all of the compounds, all of the atoms in this resonance structure are going to obey the octet rule. So in terms of ranking the stability of these ones, this is going to be more stable than this one, which is going to be more stable than this one, and this is going to be the least stable at number 4.